Today we're going to look at a problem of a ball, shown in yellow, bouncing off of a floor at an angle. We are given the angle as measured from the vertical to be 60 degrees. The kinds of things we're going to be trying to find out from this problem are: what is the net force exerted on the ball by the floor? Okay, so we're going to have to do something with conservation of momentum, and we're going to have to use the fact that the impulse is equal to the change in momentum, and the impulse is the average force times the time. So we need to put some numbers in here. So we're going to take the incoming velocity of the ball to be 20 meters per second, and the outgoing velocity of the ball to also be 20 meters per second. So notice that the ball has the same speed coming in as it does going out, but actually, because the velocity incorporates direction, the velocities are in different directions. Okay, so this is a two-dimensional problem where we're going to define the traditional x and y to be positive that way and positive that way. So first, let's find the initial momentum. Pi equals mv, and that's a vector. So notice I haven't given you the mass of the ball yet. So let's take the mass of the ball equal to 0.5 kilograms. So the initial momentum, which is a vector, is equal to 0.5 kilograms times 20, which is equal to 10 kilogram meters per second. Now we notice that this momentum has two components, an x component and a y component. So we're going to do a little bit of trigonometry to find those components. So if I draw this downward arrow right here, this is the y component. And if I draw this arrow over here, this is the x component, Vx. So in this case, we're going to go back and use our SOHCAHTOA. Okay, and we're going to write down that the sine of 60 degrees, which, by the way, this is also 60, is equal to Vx divided by 20. And the cosine of 60 degrees is equal to Vy over 20. So you notice we don't have the typical x being a cosine and y being a sine. When we solve for these, we get Vx, and remember this is the initial x velocity, gives Vx equal to about 17.3, and Vy equal to 10 meters per second. That means Px initial is equal to mVx, which is equal to 8.66, and Py initial is equal to mVy, which is equal to 5. Now we have to make sure we take into account the signs here. Px is indeed positive, but Py initial is indeed negative. Okay, so now we're going to go on to the next slide, and hopefully from the symmetry we can see that we're going to get the same results for Px final and Py final, only that they're going to be in different directions. So now we can just write down the final x and y components. Px final is also in the positive direction, plus 8.66 kilogram meters per second. But Py final is in the opposite direction. It's positive 5 kilogram meters per second. And again, if we want to redraw that second vector, right, you can see that both components, x and y, of the momentum are indeed positive. Now we are in a position to apply conservation of momentum. Or non-conservation, which we will see, of momentum. And we need to do this separately in the x direction and the y direction. So first let's do delta px. And that's going to be P final minus P initial in the x direction, which is going to be 8.66 minus 8.66, which gives you 0. And because that change in px is related to fx delta t, that tells us that there is no average force exerted in the x direction, which should make sense. Contrary, if we do conservation of momentum in the y direction, we do delta py is P final minus P initial is equal to, P final was positive 5, P initial was negative 5, so that's 5 minus minus 5, which is equal to 10 kilogram meters per second. So we do have a change in momentum in the y direction. Delta P is average force delta T. And so if let's just pick a time. Let's say that the time of the collision is, I don't know, let's pick a good number, 0.04 seconds. Then we get delta P, which is 10, is equal to average force times 0.04, which gives you an average force of 250 newtons. And notice that's in the y direction. And that should make sense because that's what's causing the ball to change its direction. And only the direction of y is being changed. A common mistake here sometimes that people tend to make is to forget that momentum is indeed a vector. And so a common error, which we hope we won't make, is to do delta P y is P final minus P initial, and to say that P final is 5 and P initial is also 5, without taking into account the sign. And if we do that, we get 0, which would mean that the force would be 0, and this is a contradiction. So, moral of the story, when dealing with vectors, any kind of vectors at all, but it comes up a lot in momentum problems, don't forget to take into account the sign.